The next talk, of course, is Bill Botkey, which was, what's the word I'm looking for, advertised very well by Ariel in the overview. So he's going to tell us how all this water is getting to Mercury now, right?
Well,
let's hear it.
Okay, so this talk is actually going to be actually surprising. It's looking at the same problem that Dana was looking at, but maybe from a different perspective. And so we'll see what you think. So I did this talk for the Micro Symposium. So this is sort of an abbreviated version. And I want to just say one thing before I get started. There's a lot of people that have worked on this problem of water delivery, and I'm a relative newcomer, and I'm still learning things. And so if I say something or I'm not giving credit appropriately, I apologize in advance. I'm sort of picking it up from first principles here. Okay, so as you know, as I think you probably know, there's evidence for water ice in the permanently shadowed regions of both Moon and Mercury or so. Okay, and if you look at the literature, you could say we could say a couple things. So the question is, how much water is in each one? We heard some really interesting things in the review talk just previously. One thing to keep in mind is that Mercury has a much larger surface area. It's almost twice as large as the Moon. So at some level, you would expect that to affect the water reservoirs you have, at least by a factor of 2 or so. But what's interesting is when you actually, when we look at the volume of space that's permanently shadowed, at least in terms of what I can find in the literature, that's about a factor of 2. So that's almost the same as what we have. Okay, but then there's the issue that the amount of water we have in each reservoir is very different. So on the Moon, it's on the order of about 2 times 10 to the 15 grams or so. On Mercury, it's at least an order of magnitude higher. And it could be actually much higher, maybe up to as much as a factor of 1,000 or so. So at the very least, to explain water delivery, we have to somehow say, why is Mercury and the Moon very different from one another? So that's what I'm going to try to address in this talk, at least looking at the ratio and the relative abundance. Okay, so what kind of impactors are capable of delivering water? Okay, so I think there's probably 3 main candidates. We have comets, and just for the sake of argument, I'm going to make comets 50% water. That may or may not be true, but it's a starting point. Okay, we have primitive asteroids. Primitive asteroids, if they're like Ci or Cm chondrates, may be on the order of about 10% water. There's other carbonaceous chondrates as well, but for the moment, we'll just assume those are primarily make up our primitive asteroids. And then finally, we have micrometeorites. So micrometeorites have a Cm, Ci, or Cr composition, and some estimates suggest that they could also be on the order of about 10% water or so. So we'll just try to take a quick look at all these and see which ones can potentially deliver the most water. Okay, so first let's talk about the impactors, the big guys. So the question is how to normalize this. And so what I decided to do is go to the Moon, and I went to the last 3 billion years of impact history. This is what we call the Copernican and Eratosthenian crater population. This is diameter on the Moon. This is a cumulative number of craters per square kilometer. So this is going to fix the population that's hitting the Moon, and then I'm going to scale that to Mercury using a model of the near-Earth object population that we just developed that's led by Mikhail Gronvik. Okay, so what we're going to assume here in this model is, according to what we got from this Gronvik model, which we published just in the last year or so, only about 2 to 3% of all the impactors on Mercury and Moon are comets. It's a very low abundance. Okay, so we have to factor that in. And then we're going to assume here, based on our model, that only about 30 to 40% of all the primitive asteroids that are hitting these guys make up the entire population. So again, it's a fair number of primitive asteroids, but remember, they have less water than comets. Okay. Now, there's a couple of assumptions we also have to make, and I'm not confident these assumptions are right, but they're the best I could find in the literature. So when you have a big impact like a comet on the Moon, you create this big vapor cloud, and a lot of this water is going to escape and never come back. So the question is, how much water actually stays on the Moon or stays on Mercury? So I found a nice plot from Lisa Ong's work back in 2010, and so she plotted here the fraction of water that's released in a given impact versus impact velocity. So you can see here for Mercury, a lot of things are hitting Mercury around 40 kilometers per second, and that produces an efficiency which is actually fairly low in terms of what's retained. It's actually less than about 1% or so. Okay, and then if you go to the Moon things are hitting probably on their own, 20 kilometers per second, and so there we're actually maybe around 10% or so. And I was a little charitable. I decided to be a little less conservative just to kind of round up to make sure I wasn't missing anything. So we'll take advantage of that. There's also the fact that once you get water on the Moon, it kind of hops around, and eventually only some of it finds its way to the cold trap, right? So this is a paper done by, a paper done by Boreas et al., and they argued that on the order of about 4% of water landing on the Moon actually gets to the poles. And because I couldn't find a comparable number for Mercury, I just said, let's assume it's the same. So Mercury could be very different, but for this talk, I'm just going to assume it's the same thing. So if we put these numbers together, so we're taking 3 billion years of impacts on the Moon, and again, that's just a ballpark number. If we went to 3.5 or 4 billion years, we'd have different numbers, right? Or 2 billion years. We're going to assume that about 1 to 10% of the water vapor in an impact that hits Moon or Mercury stays around, and about 4% of that gets to the poles. So when we put that all together, these are what we get. So in blue here is what we're trying to reach. We're trying to get to 20 times 10 to the 15th grams. Now I was going to put all those numbers over there, but it was kind of hard to read it. So I decided just to put a ratio. So if these values were 1, okay, we've achieved it. We've reached our goal, okay? But you can see that these numbers for Mercury, for both comets and asteroids, are really quite low compared to what we need. And on the moon, they're also quite low, although we're kind of getting close here for at least primitive asteroids. We're about, but on order of magnitude off, but it could be there's ways to deal with that. But still on the whole, we're low. Okay, so it doesn't look like asteroids and comets are the primary source of water if these estimates are right. Okay, so let's go now to talk about micrometeorites. And to do that, I'm going to talk about a paper that David Nisforny wrote back in 2010, which is a really nice paper. Okay, I'm a co-author on this, but this is really David's stuff. And what he did is he did a model of the Zodiacal Cloud. And that's really important for getting the flux of the micrometeorites correctly. So what's the Zodiacal Cloud? So this is sort of a picture of it, and here you can see it in the night sky. It's a circumsolar disk of small particles. So you create a small particle, it starts to evolve inwards by Poynting-Robertson drag, and it creates this dust, sort of dust signature you can see. And this is something we can actually do some interesting modeling of. Okay, so what's Poynting-Robertson drag? This is basically it's a radiation effect. Basically energy hits a particle, it changes its orbit, you can move it inward. This movie, we have semi-major axis versus eccentricity. This is just, I started a bunch of bodies very close to a Jupiter crossing orbit at high eccentricity, and you can see how Poynting-Robertson drag likes to circularize the orbits. Okay, so they come down here, wherever they go, they leave behind a green dot. So you can see they get much more low eccentricity orbits. They move inwards towards the sun. But what this means is that micrometeorites end up hitting Mercury and the moon at much lower velocities than asteroids or comets, right? On Mercury, you're hitting at only about 20 kilometers per second, about a factor of 2 less than before. On the moon, you're hitting about 11 kilometers per second. And so that means in these given impacts, you're less likely to lose volatiles. You're more likely to keep things, at least according to Lisa Ong's plot. Okay, so this is the thermal emission what we get from the IRAS data. So years ago, we had an infrared spacecraft that scanned the sky, and it actually got pretty good estimates of the thermal emission from the Zodiacal Cloud. And so what David did all this work to try to model this. And so I'm going to just give you a very quick version of what this is. So basically what he did is he modeled all the possible sources. He looked at main belt asteroids, Jupiter family comets, and different types of nearly isotropic comets like Halley types and our cloud. Then he also did an orbital evolution model very similar to what I just showed you of how these things evolved. He accounted for the thermal emission of the particles. He accounted for the fact these particles could be collisionally removed. And then finally he had to develop an IRAS survey simulator to model what IRAS would actually see here. So you put this all together, and this is the result. So the black line is what IRAS observed, okay? The blue line is what we get from Halley-type comets. And what happens is because Halley-type comets have a very broad spread of inclinations, they can produce a very broad distribution in ecliptic latitude, okay? So you can see this is not a very good fit at all with the black line. If you go to asteroids, asteroids are better than Halley-type comets, but they're much more narrow, and that's because asteroids tend to have much lower inclinations, maybe between 10 or 15 degrees or so. But again, they don't fit very well. The fit that really works is the Jupiter family comets, and they're almost dead on. So what David suggested is about 90% of all of our interplanetary dust particles are coming from not just Jupiter family comets, but disrupted Jupiter family comets. That's the only source you could have that really gets the mass to work great. So if that's correct, we now have a source for delivering micrometeorites. We know where they come from. They come from Jupiter family comets. Okay. So what we know is on the moon, and according to David's model, about 1,600 metric tons of micrometeorites hit the moon per year. And according to the same dynamical models I just showed for the Poynting-Robertson drag and the rest, about 7 times more than that hit Mercury than the moon. Okay, so we can start to put these numbers together. Now, because they're hitting at lower velocities, a lot more water is retained on both the moon and Mercury, so these percentages are higher. And again, we'll assume the same 4% reaches the poles. Okay, so if we put that together, and again, I can't say that these numbers are high fidelity, but at least they're reasonable estimates. What we found is over about 3 billion years, we get values for Mercury, which are just about what we see, pretty close to it, about 0.7 to 7. And over here, we got about between 1 and 10. So this looks like, at least, that micrometeorites can actually deliver water to Mercury and the moon and give us roughly about the right abundance, about a factor of 10. Now, I can't yet do a factor of 1,000. I don't think there's anything in the numbers that would suggest how I would do a factor of 1,000. But if you're looking for a natural difference between the moon and Mercury, micrometeorites would do this. Okay. So we can get about a factor of 10. If you want bigger numbers, we have to think of something else. Okay. And so I'll just, let's see, how much time do I have? I'll just finish up on a couple of things. So a couple nice things about micrometeorites is that we already know that they're probably an important source on the moon because about 2% of the lunar regolith is actually micrometeorites. And it has the same composition that we'd expect. It's like a CM-like material that's in a lunar regolith. Basically, it hits, it goes zap, but the highly siderophile elements it leaves behind, you can tell are from this composition of micrometeorites. So this works as a good source for water. I just wanted to say this because it's kind of interesting. That recently there was a paper on let's see, from Brooks Sayal on this dark debris. 2 minutes, okay. There was this interesting paper about this dark debris they're finding on the moon, or excuse me, on Mercury, that's associated with big craters. These big craters are actually dredging up all this dark material from depth. And so they suggest maybe there's this very big carbon-rich layer or some kind of graphite layer that's in the subsurface. Now they suggest the graphite layer might actually be primordial, and that's part of Mercury's formation. And it could be, but I wanted to see could we actually do this with, let's say, a big flux of micrometeorites in the past. So we actually looked at this. We looked at whether the late heavy bombardment itself could do it. The late heavy bombardment delivers on the order of 10 to the 21st grams of micrometeorites to Mercury. And it turns out that's enough to create about an 8-meter global layer of dark stuff on very early Mercury. I don't know if that's actually enough to create this. I think we probably need much more mass. There may be ways to getting more mass. But the zeroth order, it does suggest that there's maybe a lot of dark stuff you could have added to Mercury. And provided it didn't completely mix us in, this may provide an early source to be able to dredge back up in the surface. I just don't know if it's enough to explain what we see. But stay tuned on that. And I think that's all I wanted to say. So I'll stop there. Thanks.
Yeah, I just wanted to add that we wrote a couple of papers showing that the dust stream from Comet Encke hits Mercury every year at true anomaly angle about 30 degrees. And Comet Encke dust is Comet Encke is a low velocity comet because it's a periodic comet. So it only hits at about 25 kilometers per second. So that might be obviously a periodic source of cometary water.
Oh, I agree completely. I think at some level, David's model, I think, folds some of this in. He has to have Jupiter family comets completely disrupt. And we've actually observed this happen. We've seen comets just really fall apart in front of our eyes. That's where you're going to get most of the mass, and that's where he bases his flux on. But you could also imagine other sources that maybe are what you just described. I don't know if they dominate or not. And then there's also, the meteor streams we just heard from Dana. I think that's ultimately all folded into this at some level, but there's more to explore here. Let me say that.
Yeah, it seems like there would be implications beyond those on your slide about the water content in the atmosphere of Venus, say, or the atmosphere of Earth, that might give you other constraints. I have no idea how it would work, but that seems like that might be another data point that you would be able to play with.
Okay, so who am I thinking of?
Or you'd have to figure out why you're going to avoid it.
Yeah, there's some suggestion that if you added, for example, during the earliest days of the solar system, if you're adding a lot of comets to the Earth, you might deliver so much argon and other noble gases that we would see it, and so you could rule out comets. On the other hand, if you're delivering a lot of the material by micrometeorites, you avoid that problem because you're losing a lot of the ices, but you're still delivering a lot of the other things you need. And so it could be that's a way to do this, but we'll see.
So. Just wondering if you've thought a little bit about what you might expect on the moon from deposition like that during the late heavy bombardment.
Well, I think that's an interesting issue. I mean, the question is, yeah, if this is, so let's say the late heavy bombardment is 4 billion years ago, and you're delivering all that dark stuff at that time to Mercury, should you also have it on the moon? You might. I mean, so the question, if we don't see it, that would suggest that's not the mechanism for that. On the other hand, if the source of all that dark stuff on Mercury is something, let's say it's something that's primordial. Let's say you're looking at the earliest days of solar system history, then the moon might not be around to get that, but Mercury might. And so that could be a way you could get, also you could maybe be able to get the mass up at that point, because there's all sorts of fun things you can do in early solar system history. So, but I think that's something we have to look at. This is just sort of a fun end game slide I put in just to get people thinking.
Okay, one more very short question.
Very short. In our Polar Wanderer paper, we were really concerned about having water be stable for multi-billion years, and it's nice in the last 2 talks that nobody seems to be concerned with that. You sort of need it. But I would just like to make a comment that if you believe our Matt, correct me if I'm wrong, but if you believe our Polar Wander work, the moon's acting like a temporal history recorder, a strip chart. And in both of these works, the rate of deposition could actually be deconvolved from that history of the wander of the moon, and it would be interesting to factor that in.
Oh, I agree completely. That's why I was very excited by Matt's work, because it gives hope that you could link essentially the polar, essentially the change in the pole and the presence of volatiles. You could maybe link to mechanisms like that, and you could see if they're self-consistent, and that might allow you to like lock down the timing. It might also tell you what was going on with the flux billions of years ago. So no, I think there's all sorts of cool stuff to do with that. So.
Okay.